I'm sure by now that most people have heard the recent news about the Elon Musk company Neuralink getting the green light from the FDA to begin human trials. In case you've been living under a rock, here's a brief summary of what Neuralink is trying to accomplish.
Our initial goal is to help people with paralysis from complete spinal cord injury regain their digital freedom by enabling them to use their devices as good as, if not better, than they could before the injury.
The first two applications we're going to aim for in humans are restoring vision, and then the other application being in the motor cortex, where we would initially enable someone who has no ability to, almost no ability to operate their muscles, sort of like a sort of Stephen Hawking type situation, and enable them to operate their phone faster than someone who has working hands. But then obviously even better than that would be to bridge the connection. Take the signals from the motor cortex, and let's say somebody's got a broken neck, then bridging those signals to Neuralink devices located in the spinal cord.
We've been working very closely with the FDA to get approval and to launch our first in-human clinical trial in the US, hopefully in the next 6 months.
For once, Elon time was dead on, as that was almost exactly 6 months ago. The blind squirrel finds a nut. What you may not know, however, is that this was just one of a whole slew of announcements that were made just in the past month in the field of brain-computer interfaces, or BCIs. For example, Neuralink's goal of reanimating a paralyzed person's body may seem like a science fiction pipe dream, but not only can it be done, it has been done. Just a few weeks ago, researchers at the Swiss Federal Institute of Technology, Lausanne, beat them to it. In a preliminary sense, at least.
Scientists say it's like a digital bridge that bypasses the damaged part of his spine. Brain implant picks up the signals and sends them to a computer strapped to his back. The computer decodes it, then transmits the signal to a device in his spinal cord, triggering his legs to move.
I am in full control of what the stimulation does. And that gives me a lot of freedom, which I didn't have with previous therapy.
At about the same time, another BCI company, Paradromics, received the FDA's breakthrough device designation and raised $33 million from investors, opening the door for them to hopefully begin human trials in 2024. Their device, the ConnexUS Direct Data Interface, is inserted directly into brain tissue and will translate the intended speech of patients into text. Incredibly, Paradromics was also beaten to the punch this month, and it was done in a way that doesn't even require opening up the skull. Using fMRI scans, another group of researchers have managed to accomplish the same feat.
Researchers have used AI to translate brain scans into text. Scientists at UT Austin created a 3D view of a person's brain while they listened, watched, or imagined a story. The AI was able to read the brainwaves and translate all of that you're seeing right there into English and turn it into what looks like inner dialogue.
This is a real leap forward compared to what's been done before, which is typically on like single words or short sentences, where you can get something about the gist of a sentence or something about what a word is related to, but we're getting whole strings of text, pretty complicated ideas.
The UT Austin researchers also said that future iterations might be able to make use of more portable brain scanning tech, such as EEG, and may require less training to use as the AI becomes more sophisticated. This is particularly exciting for me as someone who has a severe speech impediment due to having cerebral palsy. It would be nice if I could just strap on a few EEG sensors and have my inner thoughts translated into a perfectly understandable synthetic voice in real time. We are already partway there, thanks to Murph. Murph is a text-to-speech AI platform. Although I still have to use a keyboard to enter my scripts, Murph takes it from there and gives me clear voiceovers to make my videos with. If you think that you might want to try Murph yourself, follow the link in the description. This video presents an overview of the basic principles behind bridging the gap between mind and machine, and the different approaches being taken to realize this goal. The BCI space is really heating up, even as other fields such as stem cell research and gene therapy are also accelerating. This gives us not just one avenue to end disability, but two. If you can't fix the problem, make a workaround. Part 1. Types of brain-computer interfaces. Generally speaking, the term brain-computer interface refers to any device which allows for the direct communication between the human brain and some external electronic device. You may have heard the terms read and write associated with this idea. These colloquially refer to the direction of information flow between the brain and the BCI. When data is extracted from the brain, the BCI is said to be reading the brain. This is a process which typically ends with the information being received as commands by some external device, such as a robotic arm or a computer cursor, that then executes the commands. In between, a series of steps transform the raw neural data into something that the device can understand. These steps are pre-processing, feature extraction, and classification. Pre-processing is necessary because no data extraction method is perfect. Inevitably, defects in the quality of the signal will arise. Luckily, these defects tend to conform to known patterns, which means that the raw data can be cleaned through various filtering techniques. Next is feature extraction, where various algorithms are used to recognize patterns in the clean data. This is the part of the process where actual meaning is gleaned. Lastly, classification is the step where the patterns that were recognized by the algorithms are translated into commands. The patterns are classified into discrete actions for the device to follow. Sometimes that device can be the brain itself, so to speak. For example, it was found in a recent study that a quadriplegic participant's ability to effectively use a BCI-controlled robotic arm was greatly improved by providing tactile feedback. Sensors in the robotic fingers sent signals to a second device implanted in the participant's somatosensory cortex, which then used microstimulation to produce a rudimentary sense of touch. This cut the time that it took to complete an object movement task in half, compared to without the feedback. When information is fed back into the brain via a stimulation or some other technique, a process called neuromodulation, the BCI is said to be writing to the brain. Most BCIs are either read-only or write-only. A good example of a read-only BCI was mentioned earlier. EEG, which is short for electroencephalogram, involves placing electrodes on the scalp in order to remotely pick up on the electrical activity of the neural tissue below. On the other hand, an example of a very basic write-only BCI is deep brain stimulation, or DBS, which utilizes electrodes implanted deep in the brain to deliver regular pulses of electricity in order to regulate abnormal neural activity. DBS has been used to treat everything from epilepsy to Parkinson's disease to obsessive-compulsive disorder. Whether read-only, write-only, or bidirectional, BCIs are more typically classified by how invasive their methods of accomplishing these tasks are. Those like EEG are described as non-invasive because they lie outside the skull. Those like DBS, on the other hand, are invasive because they are implanted directly into brain tissue via neurosurgery. The basic difference reflects an inherent tension between safety and efficacy. Invasive BCIs are much better at capturing data or modulating neural activity, since they are in direct physical contact with the neurons, but come with all the risks associated with having your head opened up and things shoved inside. Non-invasive BCIs don't have this problem, but the quality of the information that they capture is much poorer. A third group, called minimally invasive BCIs, represents a compromise wherein the electrodes are either placed on the surface of the brain underneath the skull or, in the case of stentrode, snaked through the circulatory system and embedded in the walls of one of the brain's blood vessels. Part 2. Non-invasive BCIs. There are a variety of methods for both non-invasively reading and writing to the brain. However, for the purposes of this video, I'm going to limit the discussion to the portable ones, since those are the ones most useful for compensating for and treating disabilities. Non-invasive brain reading methods can be useful for compensating for disabilities by providing an alternative route when the connection between the brain and body has been disrupted. The two portable non-invasive brain reading methods are EEG, which has already been mentioned, and functional near-infrared spectroscopy, or FNIRS. EEG is the more common one and has the widest range of applications. This is because it is safe, affordable, easy to use, and has excellent temporal resolution. EEG does have some drawbacks, however, such as poor spatial resolution, a particular sensitivity to background noise, and the fact that it often requires a saline solution to increase the electrical conductivity between the electrodes and the scalp. FNIRS, on the other hand, works on an entirely different principle. By shooting beams of near-infrared light through the head and analyzing how it is refracted as it passes through neural tissue, it tracks blood flow and oxygenation within the brain. Since more active brain areas require more oxygen, which is carried by blood, this information can be used to infer what the brain is doing. In contrast to EEG, FNIRS has high spatial resolution but low temporal resolution. It is also more expensive. Non-invasive brain writing methods are used primarily for treating neurological disorders by changing the structure and function of the brain via induced neuroplasticity. This works by first causing a short-term change in neural activity, increasing or decreasing synaptic firing in select areas. Since neurons that fire together wire together, repeated treatments eventually lead to a permanent change in the brain's physical anatomy. And, because the neural circuitry is so interconnected, these changes extend beyond the actual site of treatment, effectively forcing the brain to remake itself. The portable non-invasive neuromodulation methods are transcranial direct current stimulation, transcranial alternating current stimulation, and transcranial random noise stimulation. Transcranial direct current stimulation and transcranial alternating current stimulation, TDCS and TACS, respectively, involve the delivery of low-intensity electrical current over tens of minutes. As the names imply, one uses direct current and the other uses alternating current. Transcranial random noise stimulation, or TRNS, is the same basic idea, but, instead of stimulating at a predefined frequency and intensity, these are made to vary randomly within specified ranges. TRNS is thought to enhance the activity of neural circuits through a phenomenon known as stochastic resonance. When a weak circuit in the brain is bombarded with electrical noise at random frequencies, those frequencies which happen to align with it will amplify the circuit, boosting the strength of the signal. TRNS has been shown to boost performance on certain cognitive tasks. Part 3. Minimally invasive BCIs. As mentioned earlier, minimally invasive BCIs come in two varieties: electrocardiography, or ECOG, and the stentrode. To install a ECOG device, a hole must be drilled into the skull, and the space between the skull and the brain cleared of tissue before the device is placed on the surface of the brain. Although this does not give access to deeper areas of the brain, it is much better at collecting information than non-invasive systems, and is much less sensitive to background noise than EEG or FNIRS. Since the early days of ECOG, some companies have iterated on the idea to make it even less invasive. For example, Precision Neuroscience, which was founded by a former Neuralink employee, has only a small slit cut in the skull, through which the electrode array is slid into the space between the skull and the brain. Then there's stentrode, which takes an entirely different approach that, while still minimally invasive, actually allows for access to deeper brain regions. Here's a short clip on what stentrode is about.
What we're doing differently is using the blood vessels as the natural highway into the brain and lacing the inside of the blood vessels with electrodes or sensors that can record activity from the brain.
Those signals travel through a lead that exits out the body through telemetry unit, that goes into a computer, and those signals can be interpreted by the computer into different types of actions or commands.
We can translate these signals into switches or clicks. If a patient really wants to use the computer, for example, we can offer them a mouse click, and they can start using the mouse as they would have before they were paralysed.
So Graham can right now surf the web, write up Word documents, check his emails, do basically everything that a person normally can on a computer, using nothing but his brain and his eyes.
Stentrode's creators hope that future iterations of the device might also have neurostimulation capabilities. Part 4. Invasive BCIs. The basis of invasive BCIs is the intercortical microelectrode array. This is a grid of silicone-based microwires that penetrate into the brain tissue in order to both record from and stimulate either individual neurons or small groups of them. This setup allows for a certain level of customizability. By varying the lengths of the microwires, brain tissue at different depths can be stimulated. Also, by placing multiple recording sites along the shaft of the microwires, multiple depths can be recorded from. The name that everyone will be familiar with, in association with this concept, is BrainGate. This was a series of studies, conducted in the early 2000s, using a version of the Utah array, which was the first microelectrode array to gain FDA approval. That work paved the way for many of the advances that we are seeing now. It was from BrainGate that we got that famous video of the woman feeding herself coffee using a robotic arm. Of course, this space is now dominated by Neuralink, which puts a twist on the microelectrode array, replacing it with over 1,000 individual threads that are sewn into the brain by a surgical robot. Neuralink's approach is to have the robot cut a hole in the skull and insert the threads in one at a time, while using a combination of advanced optronics and artificial intelligence to avoid hitting any blood vessels. The threads are only a few red blood cells thick, so they trigger no immune response from the brain, and every one of them can both read and write. After placing the threads, the robot replaces the piece of skull with the Neuralink chip and stitches the patient up. The last Neuralink demo boasted 1,024 channels. However, they hope to scale that up to 1,600 by the time they start human trials. In addition to the electrical stimulation employed by microelectrode arrays and Neuralink, two other modalities exist for invasive neuromodulation: microfluidics and optogenetics. The first was developed to address the limitations of using drugs to treat neurological or psychiatric conditions. Traditional medications, such as those taken orally, have side effects precisely because they are dispersed all throughout the body. A chemical or substance which has a therapeutic effect on one area of the brain or body may have harmful effects in other areas. Also, some drugs are unable to get through the blood-brain barrier, meaning that they don't have any effect on neural circuits. Microfluidic BCIs get around these problems by using extremely thin tubes to inject microdoses of liquid medication directly into the area of the brain where they are needed. Optogenetics, on the other hand, uses pulses of light supplied by light-emitting diodes embedded along the shaft of the probes to influence nearby neurons. These three modalities have also been combined in various hybrid systems. One can easily envision a future version of Neuralink that incorporates microfluidics and optogenetics. Conclusion. As you can see, when it comes to ways to both record from and influence the brain, as well as balance safety and efficacy in doing so, we have an embarrassment of riches. The design space for BCIs is set up to be thoroughly explored. It is not hard to imagine 2024 being the year of the BCI race, as that is when many of the up-and-coming companies mentioned in this video are set to begin human trials. And even more companies are bound to pop up in the meantime. To me, this really exemplifies the principle of healthy competition. No one really knows what the best way to make a brain-computer interface is, what the optimal level of invasiveness is, or whether sticking metal wires into our brains can ever be made truly safe. The only way we are ever going to find out is by trying a bunch of different approaches and seeing which one outperforms the others. And, although I have a soft spot in my heart for Neuralink. Quite a shock, I know. My general attitude can be summed up in the phrase, "May 1,000 flowers bloom." As these companies push each other to bring the best product to market, the real winners will be the eventual consumers. The millions of disabled people who will have their conditions functionally ameliorated or cured by these devices. As I close out the video, I want to give a shout out to 2 other YouTubers in the BCI space, although many viewers probably already know them. The first is Neuralink, which covers everything Neuralink and BCI related. It is produced by Ryan Tanaka, who is a buddy of mine. He's a good guy, so make sure you check out his channel. The second channel is the BCI Guys. Their videos served as an important springboard for me as I started doing research for this video. You should check out their channel as well. Links for both of these channels will be in the description. Thanks for watching the video. If you got something out of it, then please consider giving it a like and subscribing to the channel. You can also follow me on any of these social media platforms. And, if you really like what I'm doing, you can support me on Patreon. The links are all in the description.